Now we would like to look at the dynamic viscosity. Dynamic viscosity is a fluid property. Right. The symbol that we're going to use in the class is the Greek symbol mu, and there's another type of viscosity. Actually, is a derivations of dynamic viscosity. This one is kinematic properties. Dynamic viscosity is a dynamic properties. So the kinematic viscosity is given by a Greek symbol mu, right? And the functional relationship between dynamic viscosity and kinematic viscosity is that dynamic viscosity is equal to the density of the fluid times the kinematic viscosity. So this is the first definition about dynamic viscosity. Next, we're going to look at the way that we can evaluate the dynamic viscosity, right? So we're modeling it as we consider two plate, right? Plate A and plate B. If you look from the sides, right, there will be a in two-dimensional view. We have that A at the above, and we have at the bottom plate will be another plate A, both having a different velocity, right? So let's say the bottom one we have a stationary plate, and the stationary value is about 0 meter per second, and the top one will be velocity is greater than 0 meter per second, and it's moved to the left. The reason why this plate is moving to the left because we have the force F there that act to the left. Right. So before the force being applied, the volume of fluid has a cuboid shape, and we have a rectangular cross section. Right. When the force being applied to the fluid between the plates, the fluid geometry become rhomboid atau parallel, right? So the blue one is before force been applied, and the red one when uh, the orientation of the fluid body there after the force being applied, right? So what we can say that the fluid is having a force uh, that been transmitted from the plate to the fluid. Right. So what happens is that the plate on the surface create a shear forces on the fluid. So the brown color there, it's not very nice. So it transmitted the surface forces to the fluid, and the direction will be in like a shear force. So the definition of density is then given by the shear stress divided by the shear rate. So we would like to see the similarity that we can find in solids. Right, in solid we can see that the shear stress is equal to the modulus rigidity times the rate, the angle of deformation, right? But when fluid is receiving the shear forces, the fluid will not deform like a solid, right? The solid has a elastic properties and will return back to this original shape when the force F been released. But for fluid, when the shear force been applied, it will move uh, at a constant speed, something like that, right? So we expect the behavior of the fluid will be different than. So the shear rate now is not given by the angular shape, angular, but more like the rate of angular motions. So that rate of angular motion is called shear rate. Now we look at the measuring instrument for viscosity. So the measuring instrumentation that we use to measure the viscosity of the fluid is the we call it viscometer. So this figure showing the measuring instrumentation, measuring equipment is a handheld devices. But what we look here actually um, the circle there actually is the plate that represent the plate just now when we define the viscosity, right? But this one is not in form of flat plate, but it's on the rotating disc. So we place the fluid inside the beaker, and then um, we create we are using electric motor to rotate the disc. So if you amplify the beaker, right, you can clearly see the very thin disc, right, um, that we use to uh, provide the motion inside the fluid. So normally the disc rotate at constant speed. When we set the speed, let's say for certain angular velocity, right? The motor will maintain the constant speed with more viscous speed, more force, more torque need to be required by the motor, right? So this torque produced by electric motor and then be converted into value of viscosity to be displayed in the uh, data logger. Yes, and the spinning disc, the torque we transfer to the shaft that connecting the spinning disc to the motor shaft. Now we look at the type of fluid. We plot the behavior of the fluid on the graph that show between the shear stress and shear rate, the velocity gradient. So the shear stress axis is shown by tau, symbol tau, and the shear rate with the dot to measure that it depends on the velocity, right? Now let's look back whether this concept of velocity gradient can be seen in our quiz, right? So this is the velocity profile at the inlet of the pipe. Um, so um, we show the velocity profile and local velocity in y direction. The horizontal line axis will represent the axis of the pipe, and then y is the vertical axis that connecting from the bottom wall of the tubes. of the pipe, and maximum Y will be the maximum the other apa diameter of the pipe represented by Y. As you can see that the fluid at the bottom having a zero velocity, and this one is called non-slip conditions, and we have the highest shear stress there because the gradient in X, the gradient at this location at the wall is very high compared to the rest in the fluid, right? So at the maximum at the y divided by 2 or at the center line, the velocity gradient is equal to 0, right? So if you look at uh, uh, the, the 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 velocity gradient actually is a vertical. So we have the velocity is actually at this point, there is no shear stress at the center. At the wall, we're going to have the maximum velocity gradient. Now let's look at the plot. So here we look at the characteristic of fluid. So we have Newtonian fluid and non-Newtonian fluid. The non-Newtonian fluid can be become a plastic, shear thinning fluid, and shear thickening fluid. An example of the Newtonian fluid will be like water and air. The the the, the line is straight, and that gradient that we have between shear stress and shear rate give us the dynamic viscosity of the, the fluid. So what we can say that for this plot, the gradient tells us the value of dynamic viscosity.